Raiko, sorry, I think you're muted.
Yes, Raiko, I wanted to say the same.
No. Okay. Okay, so sorry for that. Yeah, so welcome to our seminar again today. Today I have the pleasure of introducing James Fairbanks, all the way from Florida, where it's nice and sunny today, apparently. We've got a bit of sun here as well today in the UK, although in Florida this is probably the norm, whereas here it's the exception. And James is leading a project on computational category theory, which I have to say I had to look up because I didn't really know what computational category theory is, even if I have come across category theory already in my time. We just established that James sort of recently joined in Florida, having done his PhD there before, but moved to Georgia in the meantime and then back again. So we may need a graph or even category theory to disentangle that. Yeah, let's hear from him directly. He can explain to us all the things that he's done in the meantime. Okay, please, James.
Great. Yeah, so I'm happy to talk about first the AlgebraicJulia Team. So these are all the people currently working on the project. We have quite a bit of multi-institution collaboration from Topos, where you might have met David Spivak and Evan Patterson. A couple grad students at Stanford, Sophie Lipkin and Chris Brown are working on this. And then my team at the Georgia Tech Research Institute, where I was up until Christmas of this year, they're working on this project. And another graduate student, Owen Lynch, has really done a lot of implementing. So we've kind of built this team around an open source package and built this community, hopefully what grows into a community of users. So I'm really motivated in this area by scientific diagrams. So when you look at scientific computing or just scientists kind of describing models and systems and physical theories to each other, they often adopt some kind of graphical notation that they use to describe their processes or systems. So here are some examples from circuits and Feynman diagrams or signal processing block diagrams. Control theorists build these like models of their systems of systems. And then in quantum computing, this is they've adapted circuit notation and ZX calculus, which really gets you into the entry point to applied category theory. So all of these different scientific diagrams are ways that will naturally evolve when scientists are just trying to communicate with each other. They draw pictures of their models, and that's it's our job to kind of figure out how to give these treat these diagrams as a graphical syntax that have mathematical semantics, right? So all the visual elements in these diagrams have some mathematical meaning, and so we can. This has been formalized within the applied category theory community through the language of string diagrams as formal graphical languages that have precise mathematical semantics, and that's kind of the application of category theory. So circuits, signal processing, chemistry and chemical reactions, manufacturing processes, control theory, engineering design. These figures are all taken from a textbook, an ACT textbook that I'll be using to teach in the fall, an applied category theory course here at the university. So all these different string diagrams, they have different graphical elements in them that correspond to algebraic structures in the corresponding categories, be those kind of hypergraph categories that Pavel was talking about a couple weeks ago in this seminar, or compact or dagger compact or whatever they are. That corresponds to different types of graphical syntax. And so the benefit of viewing things with string diagrams is that we get great abstractions, for example, that translate between disciplines. For example, we can use string diagrams to represent proofs with inequalities, kind of arguments you'd make by chaining together a bunch of inequalities. You can represent these as a string diagram, which is a computational object. So here, a string diagram represents the idea of a proof that given proofs of the interior boxes, the blue, orange, and green inequalities that state t is less than v plus u, w plus u is less than x plus z, v plus x is less than y. If I have proofs of these hypotheses, then I can construct a proof of the conclusion, which is what the outer box represents. So kind of wires carry values, be they, say, real numbers. The boxes represent inequalities. And then the monoidal product is two wires in parallel mean the sum of those two values. So that's string diagrams in a monoidal preorder correspond to proofs of these inequalities. But the very same abstractions can get reused in reasoning about chemical systems, where if I have primitive chemical reactions, here again shown with boxes, then I can assemble that into a compound reaction by kind of chaining how the molecules flow between the different reactions. And so this very same abstraction of string diagrams in a monoidal preorder give us an automated reasoning system for, like a proof assistant, or a chemical reaction designer type thing. So that's kind of the flavor of why we care about these category theoretic abstractions, so that we can build software that translates between different disciplines because it gets the mathematical abstractions correct. So Catlab is a piece of software that implements this vision, and it does so in kind of three layers. So there's a theory layer, which is based on the idea of a generalized algebraic theory. These are equivalent to essentially algebraic theories, which you might be more familiar with. But generalized algebraic theories kind of mirror the way mathematicians talk about mathematical objects and theories of these objects. So you have types, terms, term constructors, type constructors, and axioms in the theory. Then we have a variety of syntaxes, which you might think of as initial algebras for these theories. And these syntaxes are like a formula notation, a string diagram notation, and a programming language syntax notation. And they all have different benefits. The formulas are easy to manipulate with term rewriting. The wiring diagrams are easy to visualize, right, and understand what these formulas mean by drawing pictures of them. And then the domain-specific language is easy to write. Programmers are very familiar with how to write programs. It's kind of their whole gig. And so that's much easier than writing these kind of point-free notation tensor product formulas. So we have the theory, then we have the syntax, and then we have instances where we connect to the Julia data structures and Julia functions. So kind of connect up to the real world of the programming language where actual computation happens. So everything in the theory and syntax is symbolic computation. And then at the instance level, it's either combinatorial or numeric computation. You actually have arrays of numbers and you manipulate these arrays. So theory, syntax, instance. The instances are like models of the theory. So one huge class of ideas from category theory that we've found very useful is the notion of copresheaf categories or CSets, where you've got a generalization of graphs that are particularly well behaved. So graphs are ubiquitous because they're very simple and they're very useful, right? So a graph is just a set of edges, a set of vertices, and these two maps, the source map and the target map. The source map assigns for each edge a source vertex. The target map associates to each edge a target vertex, which we interpret as the head and tail of an arrow in a graphical language. So if you have this indexing category, GR, the parallel arrow category, the GR sets are your regular everyday notion of graph. If you're a category theorist, which means directed multigraph. So the reason we like this is that kind of for any finitely presented category on the left here, you can look at functors into set and you'll get some notion of combinatorial data structure. So for example, here, this schema that has four objects and 4 arrows, it's kind of a pair of spans that share the same feet in code directed bipartite graphs, or what's known as whole grain Petri nets. And these, we use them to model chemical reactions or epidemiological systems. So that kind of S is the set of species, which we draw as blue circles. T is the set of transitions, which we draw as orange boxes. And then this span encodes the wires that go from, the edges that go from transitions to species, the other way around. One span encodes arrows that go from transitions to species, and the other arrows that go from species to transitions. And so that's kind of why it's a directed bipartite multigraph, if you wanted to spell it out like that. So yeah, CSets are objects of a category that has it's this functor category from some finitely presented C into set. And generally, this works for any small category C. Because we're actually computing things, we need the indexing category C to be finitely presented. And we need all of the sets that you map to also be finite. So objects go to sets, arrows in the indexing category go to functions between those sets. So these things, CSets generalize tables and graphs. So to generalize or to view a table as a CSet, you have one object that represents the index, and each of the legs represents a column. So in this span, this multi-span, I should say. So this is like a table of categorical data. And the arrows are mapping for each row. The ith arrow sends each row to the ith field of that row. So that's how you could model kind of a single database table. Then graphs we've already seen. It's kind of this two parallel arrow schema. We can go get a little fancy and do weighted property graphs, where you have each edge now has a weight and each vertex has a property. And these come from some finite sets of weights and properties. Then here are just some more flavors where you've got discrete dynamical systems. So you have one state space and a map from the state space to itself, which picks out for every state the next state. So that's how you would describe a discrete dynamical system. Then you can kind of like do push outs of schemas here and kind of merge things. And so you can talk about or just combine things, right? So DDS happening on a graph. So I have a graph, each vertex has a state, each state has a next state. So you could think of that as storing all the data of what would happen when a discrete dynamical system occurs on a graph. Then open circular port graphs are real fancy version of graphs where you've got vertices have ports, and then there's an open boundary around the whole thing. These are useful for describing conjunctive queries or tensor contraction networks or expressions in regular logic. These can all be represented as open circular port graphs. So for a mathematical flavor of thing, kind of geometric in nature, we have support for semi-simplicial complexes, and there's like a kind of a table of like simplicial versus semi-simplicial, complex versus set. So the semi-simplicial sets correspond to the combinatorial information in a discrete discretized manifold, which we use to implement meshes. So there are presheaves over this schema. We have some set of triangles, edges, and vertices, and the pointer. You have triangles, edges, and vertices, and you have relationships. Each triangle has 3 edges. Each edge has 2 vertices. That gives you a notion of a mesh. So we've built quite a bit of software around these meshes in combinatorial spaces.jl, which is a Julia package for building simulations. So I've talked about the objects and given some examples of CSets. The homomorphisms come from natural transformations. So you've got a functor category, so the objects are functors, and then the question is like, what are the morphisms? Well, they're going to be the natural transformations between those functors. So what that says is that each CSet homomorphism has components, one for each object in C, and then for every arrow in C, you have to satisfy an equation that generalizes the graph homomorphism equations. So if I have to map edges to edges and vertices to vertices, such that the source and target of every edge is preserved by this mapping. And now that generalizes from just graphs to any CSet. So here's how this grinds out in implementation. There's also some facts about CSets. They're Topos and an adhesive category. And since they're adhesive, we get all limits and colimits exist, and DPO rewriting will work. You can compute push-out complements. You can set up double push-out rewriting rules, and we'll get to that in a little bit. So I wanted to highlight that composition of natural transformations happens component-wise here. So if I had a CSet morphism alpha that sends X to Y, and a CSet morphism beta that sends Y to Z, I can compose them component-wise. So first I map the edges of X to the edges of Y, then I map the edges of Y to the edges of Z, and I compose those 2 maps to get a map from X to Z. I do that, I compose all my maps component-wise, and all of my naturality squares, I paste them next to each other to get the naturality squares of the composite morphism. And that principle that everything that you do with CSets, you do component-wise, is generally true. Not everything reduces strictly to component-wise stuff, but that's the place to start when you're implementing. And so here's the example for graphs kind of worked out in Catlab code. So we got some imports up here. Then you declare a graph with this macro that defines a domain-specific language for specifying CSets. So you say it's going to be of type graph. So it's got 4 vertices and 5 edges. And here are the source and target maps. So if you take these 2 arrays together, that's the edge list encoding of a graph. So the edge from 1 to 2, the edge from 2 to 3, 3 to 4, 4 to 1, 4 to 2. So this notation generalizes the notion of edge list to arbitrary schemas. This gets rendered into, parsed and loaded and converted into a little in-memory database that stores all this information in the form of tables, where each object in C becomes a table, each arrow becomes a column in that table, and it's like a foreign key into another table. So we wrote a little in-memory database to do this, and then you can print it out as tables. And we generally try to have support for just calling GraphViz on any object in Catlab, and you should get a picture of it. Doesn't work. It's not fully automated yet. You do have to kind of tell Catlab when you introduce a new data structure, you have to tell it, like, here's how I want you to draw instances of this data structure. So we know how to draw graphs, kind of the normal way. So here are a bunch of varieties of graph that I think, and I sometimes getting involved in this graph rewriting literature, get a little confused. People say graph and they mean some kind of variety of graph. So what's nice about this perspective is that it lets you use a graph to precisely describe the kind of graph you're talking about. So you write down this schema, and the schema is just a graph plus a list of axioms that have to be satisfied. So I didn't write any of the axioms down, but in this case, they're kind of obvious. So regular graphs have source and target. Reflexive graphs have source, target, and a reflexive edge. So for every vertex, there's an edge that represents the self loop at that vertex. Then we have symmetric graphs where we have source and target, and an involution on edges that tell you for every edge, there's a reverse of that edge. There's an edge going in the opposite direction. And that being an involution means that the edges are paired up into their, so you have like two directed edges that go in opposite directions, and they get paired up into one undirected edge by that involution. So then you can combine these two theories of graphs into reflexive symmetric graphs by just kind of merging these two schemas. This is actually a push out in the category of graphs, which is pretty cool. So you get reflexive symmetric graphs. And the morphisms between the whole algebra of homomorphisms is defined by the schema. So when you change the schema, you change the morphisms. And when you change the morphisms, you change the categorical products here. So that kind of the way in which you can talk about the product of two graphs changes depending on the schema of graph that you're talking about. So here I've shown the product of the path graph with itself in each of these four schemas. So kind of, if you have an intuition like mine, you'd say that whatever the grid is, like if I needed to give a definition of a grid, I would define it as the product of two paths. That should be the grid. And so in these different notions of schema, you get different notions of grid, which is interesting. So another example is compiling kind of notions like a colored graph into schemas here. We can talk about the path graph. It's kind of like a reflexive path graph with two colors, alternating colors. And when you take products, you multiply the set of colors. So you go from 2 colors to 4 colors. So I want to move on to talk a little bit about implementation here. We've got, this is the implementation of taking arbitrary limits over arbitrary CSets. So this code is quite short. It fits on a slide. Of course, talking about the length of code, like there's a lot going on in these subroutines we're calling. But the generality is kind of, we're iterating over the arrows in the limit diagram, and then we're iterating over the arrows in the indexing schema and computing a bunch of limits pointwise there. So then, and then you've got to like pack components. So there's like unpacking to do things component wise, and then packing up the components into the, like bundling everything together. Right? So this lets you think of the way you think about a CSET algorithm is like, for all objects in C, I do something with these finite sets. For all arrows in C, I do something with these finite functions, functions between finite sets, which are just arrays. And then, so you kind of like iterate over all the components, and then you bundle everything back together. And so that lets us implement algorithms at a level of genericness that I think most software does not have. And then I also want to point out that we encode the description of the indexing schema, which is a graph. We encode that description into the Julia type system. So kind of our types, the types that represent CSets are dependent on a value in the category of graphs. So that's pretty cool. So not only do we have limits, we also have colimits. So you can kind of write out some graphs using a kind of imperative interface. You can write down CSET transformations. So I have to map vertices to vertices and edges to edges. I have to tell you the domain and the codomain. So I can take two CSET morphisms with the same domain, and I can compute a push out in that appreciation category. And so that lets you glue graphs together along vertices and edges. One of the big change in the perspective to CT is that we focus not on objects, but on transformations, structure preserving transformations between those objects. And so kind of like group theory is not the study of groups, it's the study of group homomorphisms. And graph theory isn't the study of graphs, it's the study of graph homomorphisms. That's kind of the CT perspective. And then when this like grinds out into code, that means the user isn't just writing down graphs, they have to write down graph homomorphisms. Just a little bit more data. It's kind of the data of two graphs plus a list of vertices and a list of edges. And but the reward is that we can give them constructive algorithms. You know, constructive mathematics becomes easy to implement algorithms. You kind of can read the formula for a push out or for a colimit and just write it down in Catlab code. So I want to move on to rewriting now that I've kind of given you the introduction to CSets and their general representational power. So hopefully Dr. Chris Brown defended his dissertation yesterday. It was on West Coast time, so I haven't checked in with him yet because it's early morning here on the East Coast. So I hope it went well. And so I'm not prematurely saying doctor. But he is a student in the adjoint school this semester, which is a thing run by the Applied Category Theory Conference, where they introduce senior undergraduates and graduate students to category theory and its applications in the form of an ongoing semester-long program, and then a week of usually in-person, hands-on mentoring and research activity. This year it's all virtual, and Chris has been doing that. And so his little adjoint school project has been rewriting for CSets. So you implemented graph rewriting, and this is how it looks in Catlab. If I want to, I express my rule as a span, and then my match as a morphism. I compute the push-out complement to get the context, the embedding of the context for the rule into the input graph. Right? So then I compute this other push-out, this double push-out. Here's one push-out, here's the other push-out. So the computational primitives you need are push-out complement and then push-out. Yeah, so here's this example kind of worked out in Catlab notation. So you've got this graph, they're laid out visually. So you write down your rule as a span of graphs, and you write down your match, you ask for the push-out complement, and then you can do the rewrite. So this is what this code looks like. It's kind of tedious to specify all this stuff by hand. So that's an area that we need to tie up some loose ends around graph rewriting. So yeah, so Chris has been working on this, just the last couple weeks as part of the adjunct school. So I want to talk about string diagrams, where I'll first show you how we were doing string diagrams before Pavel's talk in the GReTA seminar couple weeks ago. And then I'll show you the Catlab implementation of Pavel's approach. So this is how we were doing it, which you might think of as port graphs with interfaces. So you've got a set of boxes, set of imports, outputs, inputs, outputs, and wires, 3 sets of wires. The imports and outputs both are attached to boxes. And then the inputs represent the incoming wires, or like the places where incoming wires can attach. So the domain of the string diagram. And the outputs represents the codomain of the string diagram, where wires can leave the diagram. Then W-in are like these wires that come from the domain, and W-out are the wires that leave, and W are the internal wires. So it's kind of clumsy to handle, 4 different types of ports and 3 different types of wires. But when you implement algorithms involving string diagrams, you often need to handle the in wires different from the out wires, different from the internal wires. And so having that kind of case, this schema turns a case statement in the algorithms into like different objects in the schema. So you're kind of baking something into the schema directly. So Catlab is all based on embedded domain-specific languages. So we have a DSL for specifying monoidal signatures. And so this is a pretty simple monoidal signature here. I'm going to have 1 generating object and 3 generating morphisms. So F from X to X, G from X to X, and plus, which I'm going to think of as a monoid, X cross X to X. And so this gets rendered in Catlab, and I'm going to think of this as a free Cartesian category generated by these generators. So this gets rendered into code in this very direct one-to-one translation from how you'd see the monoidal signature written down in a paper. Then, so once you've written this presentation, Catlab generates a new domain-specific language for you to write string diagrams in that monoidal signature. So now I can say I have a program in this presentation I called prog, and that's going to have 3 input wires, each of type X, ABC. That's these input wires. Then I'm going to call F on the first wire, G on the second, and F on the third. That's these 3 boxes. And then I'm going to apply G to the output of F, and I'm going to do some addition. So I'm going to add these outputs, then I'm going to add those outputs. I'll return the sum of these values. So what's nice about this DSL is that it inherits a lot of the programming language syntax from Julia, which is a Lisp, kind of an M expression based Lisp. So it's very easy to write DSLs in it. And it's got a pretty flexible expression based structure syntax. So we get lots of cool features, like we kind of call functions on functions. We have tuple types. And then the kind of doctrine of category that you picked, here we picked free Cartesian. What that means is in this program, I'm allowed to reuse variables without an explicit copy. Kind of this language implicitly understands if I were to reuse a variable, I would want to kind of copy that wire. And that would be allowed. If it was just a free symmetric monoidal category, that would not be allowed, and I'd have to explicitly copy this. So, I'd have to, sorry, let me say that again. I'd have to introduce a generator that allowed me to copy specific objects. But here in a free Cartesian category, I copy it. So the point here is that I have my mathematical notion of a monoidal signature. I can translate this directly into Catlab, and then I get a domain-specific language for writing string diagrams in code, which is very useful. So here's how Pavel would do this instead, based on his talk a couple weeks ago, which I was not familiar with until that talk. So it's pretty cool that I was able, with a lot of work by Chris, we were able to get this working and just since that talk. So yeah, I've got my signature. I can compile that into a hypergraph over this hypergraph schema. So I have kind of E11, which represents my arity 1, co-arity 1 morphisms. I have my object E21, which represents my plus is kind of a 2-1 morphism. It has 2 inputs and 1 output. And they both, all my variables are going to be represented by this set V. Each morphism has the appropriate number of arrows to V. So you're kind of like source and target, source 1, source 2, target 1, representing this relationship between the morphisms and their arguments and co-arguments. So here's what the schema looks like as a picture. This gets compiled into Catlab as this code. So you write down kind of, here are my 3 objects. One of the nice things about Julia is that we have Unicode in variable names and function names. So we can kind of directly translate math notation that way. And so I've got 3 objects. This data and attribute thing let us put Julia values into our CSets, which kind of extends the theory of CSets a little bit, but it's super useful. So we've got 3 objects, then we've got these 2 morphisms, or we've got several morphisms, 5 specifically. We've got S and T, which represent the input and output of the 1-1 morphisms, S1, S2, T1, which represent the inputs and outputs of the E21 morphisms. And then these labels let us put names on things. That's why that's useful. So an instance of this schema is the hypergraph that encodes the monoidal signature here. So this is how you'd write down you translate this monoidal signature into this hypergraph, which you can think of as these tables. So the labels come in because we want to be able to check that the function names, the morphism names, get encoded into this data. So then we can take slices over this hypergraph schema and get exactly what you'd expect. So I think this is a general principle. We haven't, if somebody knows this fact, I would greatly appreciate it if they gave me a citation for it. The idea that like CSET morphisms can be encoded as CSETs of a bigger schema. It makes sense because kind of the CSET morphism is like 2 CSETs plus a bunch of functions that satisfy some algebraic equations. So like, should be a bigger CSET. So that's how we've implemented it, but I don't have math to back that up. So you want to, this is how you represent CSET morphisms in this monoidal signature, and then slices are elements of this schema. So this would be the string diagram we had represented as a slice over this guy, this object, its morphism to this guy, where the colors, I've encoded the natural transformation by assigning colors to elements of H. So the orange boxes go to F, the green boxes go to G, and the aqua circles go to plus. Every wire in the string diagram becomes a vertex in this directed hypergraph. This is what this looks like in code. We've got the schema shown in code and graphical. We've got the base of our slice, the element that's over it, and then I had written down the transformation on the previous slide. So with that in place, we can do rewriting in CSets. So, that already existed before Pavel's talk, but this can be applied to the hypergraph formulation there. And so we can kind of associate this plus directly. So I've suppressed the middle part of the DPO so that it could fit on the slide. But yeah, so we want to find this pattern in this hypergraph, and we want to replace it with this pattern to get this hypergraph. And that all works. So I think there's an open question here comparing there's different approaches to schemas, or different schemas for string diagrams, I should say. So kind of our port graph thing, it's not aware of the monoidal signature, and it doesn't bake any of the arity preserving nature into it. This hip sigma, which you can also use to encode the same monoidal signature, string diagrams in a monoidal signature, this approach, it bakes the arity preservingness into the morphisms, and I think in a very useful way. So I think there's a design trade-off, a design space here, and that from a computational perspective, this is something interesting and worth exploring. Are they equivalently representable? Can you translate one into the other? All of those kinds of questions. But yeah, this notion, this connects back to what I was saying earlier about the different types of products between graphs. Like, you bake this way of encoding a monoidal signature as a hypergraph bakes the arity preserving nature of the morphisms into the schema. So another way of encoding monoidal signatures into CSets was given by Joachim Koch at last year's ACT conference in this whole grain Petri net paper. And so we've been working on this for, since he presented it. Has this like Topos representation is what he calls it. It's for species, inputs, transitions, and outputs. Species, Topos. And this is the schema, and we can represent the same hypergraphs as instances of this schema, but now the arity, the morphisms in this functor category are not arity preserving. So he introduces this whole notion of etal maps to get that arity preserving nature. So I think there's another open question there comparing these two formulations, the whole grain Petri net approach versus this slices over hypergraphs approach. So we've been using these Petri nets to represent epidemiological models and also chemical reaction networks. So I want to show my goal, I'm not interested in rewriting for rewriting's sake. I'm interested in all of this for the purpose of building scientific modeling tools that are very robust, generalizable, generic, reliable, introspectable, have all these great properties for scientists, easy to use, easy to build, easy to reason about. I want to build scientific computing platforms, and the CT abstractions give us a good basis for tool building. Graph rewriting lets us do something that I think of as model space exploration, where I want to take a model like the SIR model, which is over 100 years old, or almost 100 years old, model of pandemics or epidemics. And so you just have three states: susceptible, infected, or recovered. And you have two rates, the infection rate and the recovery rate, and that fully characterizes the dynamics, and the dynamics look like this. That doesn't capture a lot of real diseases. The infections are too quick to start and too quick to end. And so the epidemiologists introduced the SEIR model, where you now have this exposed phase that once you are exposed to an infectious person, you don't become infectious immediately, you become exposed. And then there's some rate at which exposed people become infectious over time. It's like the incubation period of a disease. Then SEIRS handles diseases that are endemic, where people can get them multiple times. Like the common cold, you can get it every year. So that's something like SEIRS, where you can return to being susceptible. Then SEIRD for handling diseases that have a fatality outcome. So all of these different models can be captured as rewrites of the original SIR model in this category of Petri nets. So here's a link. You could and these slides will be available after the talk. You can go find these rewrite rules on a GitHub page. So yeah, so I'll just briefly show some other applications and then be ready for questions. Yeah, so there's a spectrum of scientific computing technology, from analyzing arbitrary code to computer algebra systems. And these modeling frameworks and domain-specific languages live in between. That's where we want to study things. And we want to build tools where there's this problem where different modeling types, be it probabilistic models, mechanistic models, machine learning models, optimization models, they all have their own tasks you have to do. Calibration, selection, comparison, verification, validation. There's kind of this n-squared problem where for every modeling framework, I have to implement all the modeling tasks. We want to reduce that, just like how with CSets, we're able to implement limits and colimits and rewriting for all indexing schemas. We want to be able to implement calibration, selection, comparison, verification, validation for all modeling frameworks simultaneously. So we really need powerful abstractions if we're going to do this. So our modeling pipeline is that you have some syntactic representation of the process. You want to build a specification of systems that exhibit these processes, translate that into some numerical or mathematical representation of the problem, and then solve it. So yeah, the Petri net rewriting lets us do this. Yeah. So with Petri net rewriting, we can build these big models. We can represent epidemiological models as Petri nets, and then things in categorical constructions in the category of Petri nets give us things like product models. Limits and colimits let us build big models out of little models. And so you can model kind of a 3-city epidemic by taking a model of the disease. This is SIRD, it's the SIRD model, and a model of 3 cities. And then you can build this model of SIRD occurring on 3 cities. And this plot doesn't match. This is the plot for SIERD on 3 cities. So here's the example built out for turning a SEIRD model into a geometry, like a spatially diffused version of that model. So we wanted to model kind of 2 cities with a kind of suburban corridor between them. So this, in the US, you might think of this as like Baltimore, Washington, where you've got a big city in Washington, DC, and a big city in Baltimore, and kind of a little strip of population that lives in between them. And so what happens is the infection starts out in Washington and spreads rapidly throughout that city, and then traverses up the suburban corridor, which in this case is this being a European audience. Geography doesn't really, you're not familiar with this geography, but the idea of 2 cities separated by corridors happens all the time. So yeah, you've got this pattern, and we're able to automatically construct what would you typically think of a partial differential equation model from an ordinary differential equation model by making assumptions about the spatial dynamics. So we're able to kind of rapidly assemble these models that would normally take a lot longer, and we do it because we're representing the scientific models in this kind of functorial semantics way, where you have a graphical syntax for describing the models, and then a mathematical semantics that lets you simulate the models. So yeah, getting closer to this vision, and then conclusions for this particular talk are that category theory provides abstractions useful in multiple domains. Our implementations in Julia leverage a lot about Julia to be expressive and to be highly generic code. That's also, I didn't talk about benchmarking, but this goes pretty fast. And then hopefully CSets provide fundamental infrastructure for compositional computing that we can use in lots of different areas. And rewriting, just presenting an implementation of CSET rewriting, which hopefully generalizes a lot of the graph rewriting stuff that you guys are interested in. So yeah, that's my talk, and I'll be happy to take any questions.
Okay, thank you very much, James, for that interesting talk. So we have a question on the chat, but before we go there, because I mean, this is about Khan extensions, but I have a slightly easier one first. I was trying to understand by analogy the difference between the encodings of string diagrams that you mentioned, between the one that you had originally and then that you stumbled upon after Pavel's talk. And I was wondering whether it's similar to the difference between, for example, bipartite graphs and hypergraphs in the way they are modeled mathematically.
Right. So,
I mean, just by analogy, obviously, it's slightly different.
Yeah, I think about this a lot, and so I think it is relevant. So when you say hypergraphs, you're talking about like a subset of the power set of the vertex set.
Well,
right?
If they are unordered, yes, but they could be ordered in which case it would be sequences. But
yeah. So to be full combinatorialist, nothing is ordered, and everything is symmetric, and so hypergraphs are like very disordered things. There's just like so many of them, and there are no rules, and so people study like specific types of hypergraphs. They think about like k-regular hypergraphs, where every hyperedge has k vertices, where they think about simplicial complexes or simplicial sets, which are a certain type of hypergraph where you have all the closure relations, that triangles have edges and edges have vertices, and tetrahedrons have triangles, all that. So you always, whenever you're trying to think about hypergraphs, you kind of have to constrain the space. The bipartite graph version of a hypergraph, where you think of one part as the vertices and one part as the edges, as the hyperedges. That very much tracks the Joachim-Cox view of whole grain Petri nets. The version I just talked about, where you think about like k-regular hypergraphs, that tracks the monoidal signature, the hip sigma approach, where you bake in the arities into that. So if like a k, I'm gonna actually use my whiteboard.
Yeah.
A k, or my chalkboard. If I had like a 3 regular hypergraph, it would be like this. And then the analogy of 2 going this way, 1 going that way, is the directed version of kind of, I'm baking the arity of the hyperedges into the schema.
Yeah. I mean, in my version of hypergraph that I would normally consider, the signature is basically a family. You have a family of hyperedges. So you have I'm not making sense. You have a family of hyperedges have arities.
Yep.
Yeah, and every arity gives you a different type of hyperedge. So you get a different set in your signature, a different sort in your signature for every. So you basically get a family of sorts for the hyperedge. So like your E2-1 there, that would be one particular example of a type of hyperedge. Exactly. Yeah. Okay,
So I think that's the avenue for exploring these, is like there's a whole class of techniques I didn't really talk about, functorial data migration, which lets you think about morphisms between schemas and move data between the schemas. So kind of morphisms between C and D induce morphisms between, or functors between C sets and D sets. Oh, there's like covariant, contravariant one. So I think that's the right avenue for how do you reconcile these two approaches.
Okay.
In a sense, like you're forgetting the arities when you go to the directed bipartite graph version.
Yeah, and they're no longer preserved by the morphisms, therefore, isn't it? So
right.
Well, I mean, that's as you say, the morphisms are more important than the object. So there you see the difference.
Right. Yeah. So for string diagram rewriting, you really care about like preserving these arities. It's like super important. So it makes sense that you'd bake it in to the indexing schema to do it that way.
Okay, so Nicholas, Nick forwarded the question from Frank Center asked on YouTube. Can you read that? So what about left and right Kahn extensions of functors?
What about left and right Kahn extensions? What about left and right Kahn extensions? That's something that we do not currently have implemented, but would be a natural extension to think about. So I think that if somebody knew a lot about Kahn extensions and was ready to dig into the code, I know especially Owen would be very excited about implementing this.
A couple of people raised their hands. I don't know whether that was because they wanted to say something about that particular question, Andrea and someone else. So you want to?
No, I had another question.
Okay. All right, but I think we've covered that one.
I can just quickly address this Alan Ransel's question about theorem provers. I think that rewriting, does push us towards theorem proving, and so I do think that it might be worth it to delete that from the README. The Catlab README is from a time when theorem proving was not going to be there. And typically, when you say, I'm doing category theory and computer science, people are like, oh, so like Haskell and Cartesian closed categories and monads are endofunctors or monoids in the category of endofunctors. And like Catlab is not that. It's very much a different perspective on applied category theory and a different way of doing categories in computation. And I think this copresheaf story about CSets really captures that notion of like, you get functorial semantics, you have theories and models and morphisms and all, constructions like products and coproducts and all that stuff. But you don't have a Cartesian closed structure. At least you're not focused on it. You're not viewing it as a model of computation. I think that's part of the nice package of this story. I just realized now the person who was nodding vigorously is the person who asked the question. I was like really jamming with your nodding, aggressive nodding, and then like, oh man.
Yeah, thanks.
He didn't ask.
Yeah, I mean it'd be great to explore more. Thanks.
Thanks. Andrea, do you want to ask your question?
Yes. James, first of all, thanks for the very nice talk. Really very interesting. So it happened that some decades ago, I don't say how many, I was confronted with the theory of left exact sketches because of some constructions I was trying to do in my thesis. And I made a construction on left exact sketches, which was at the time extremely useful, and of which I didn't see trace in your presentation. That I also think would be very interesting also for you. And you spoke about making a product of two schemas, right? Showing the difference that you get in multiplying a schema for paths with different kind of graphs or schemas of graphs. Okay, but there is a tensor product on sketches, which is extremely useful. And one For example, you can get immediately one of the things that you mentioned in the talk as an easy construction that you can do. For example, the fact of modeling morphism of hypergraphs, okay? And the tensor product of two sketches has this property that if you take the models of one of the two, so basically the models of the tensor product are exactly the models of one sketch in the category of models of the other sketch, okay?
Oh, that's cool.
Opposing models, which is, I think in your context should be extremely useful. For example, if you take you can have a sketch for morphism, which is just two nodes and an arrow between them, okay, which has as model or all arrows in a category. If you compose these with the tensor product with the morphism, with the sketch of graphs, you get exactly a sketch for whose models are morphism between graphs. Okay?
Oh, that's exact. This is why I put that slide up, because I'm sure someone here knew the answer.
Yes.
So, okay.
So the general construction is very useful. It's not the categorical product of sketches, but is a tensor product which doesn't have the universal property and which is pretty easy intuitively. Essentially, you take the product of the objects, but then you don't have all composite arrows. You have like a grid of arrows in the composite sketch, where the vertical ones are those from one sketch, the horizontal one are those for the other sketch, and then you require the tall squares commute.
Right.
This gives you for free. For example, I use this to take I don't know the category of internal categories in the category of monoids. You can do this by composing the two sketches very easily. Nice. I think it's extremely useful in your context because you work a lot with these left exact sketches, and this gives you a sort of compositionality of models.
Yeah, that's great. I'll definitely look that up. And we've had kind of souping up the indexing schemas to go from kind of just plain categories, plain categories to like sketches, like finite limit theories or something like that, so that you can talk about a pair of edges where the target of one is the source of another, stuff like that. So moving up to left exact sketches and this tensor product sounds like exactly the right thing that we need. So yeah.
Yeah, so this clearly applies also to finite product, and clearly you present the models just as a graph, a finite graph, but actually you also have equations for your models, I guess, right?
Yes, because we do have the equations.
Instead of the structure that you described, you need equations to get a meaningful notion of model. Okay.
Yeah.
I will send you the link to the paper from which I learned this notion of. Is a paper by Gray, published in '89. So 89. I will send you the link to.
Yeah, that's great.
Okay.
So.
Okay.
Great. Thank you so much, Andrea.
Thanks, Andrea. William has a question, not about Khan extensions.
Yes, hi. Thank you very much for your talk, James. I enjoyed it.
Thanks,
this is a much more applied question and has nothing to do with Khan extensions.
Good.
So, I mean, it seems. I mean, you're thinking about graph rewriting. It looks like it sounds like very much in terms of rewriting. For the epidemic models, rewriting the transmission model, right? Saying how can I get a different transmission model from this one, and that's I mean that itself is super useful, especially with especially with the going to PDEs and that sort of thing. Yeah,
it puts a spatial structure on the set of all models, and so you can talk about models that are near other models. That's kind of that's why we care.
Yeah, but my question is. So sometimes what you might like to do, and sometimes what we do is we imagine, for epidemics, we imagine that the population itself can be represented as a graph, right? Where, an individual, say, is a vertex, and there's an edge between two individuals if they're in some kind of contact. Maybe they live in the same house or go to the same school or something like this, right? So
and I should say before the rest of the question, we have an agent-based semantics for our Petri nets that simulates the transmission dynamics in a kind of stochastic way. So
right, but do your agents have edges between them, or are they kind of all bumping around in a?
Yeah, they're mostly bumping around. But the product model thing that I talked about would put edges between them. It would be like groups of agents that have edges between them, that have connections between the groups. But,
yeah. But okay. I mean, my question was, like, you can do this kind of dynamics as itself a graph rewriting system, right?
I'm not familiar with that at all, but I am excited about it.
Right. Okay. So my question was, do you have thoughts on how that could work and how to do that efficiently and so on?
So I have thoughts that are currently forming, in that now that we have graph rewriting, I think we could represent it that way. Represent the agent-based version as a graph rewriting problem, where basically take the colored graph, and now the color is the disease state, and the sub patterns are like, if I'm infectious, if I have one infectious node and an edge to a susceptible node, I can rewrite that to two infectious nodes. And so you could compile the Petri net representation of the disease dynamics into DPO rewriting rules for your colored graphs. And I think you could sit down and do that right now, given all the infrastructure that's there. I think you could sit down and write that up in a couple hours. Maybe a couple, especially if I was working from a formulation of SIR as DPO. So it sounds like the paper you're currently working on.
A little bit, yes. Although without nearly so elegant a formulation in code.
I think, I hope our CSET infrastructure is like, it really should let you implement all of these variations on graph rewriting in one coherent picture, as long as you're like the bells and whistles you attach to your graph are things that can be described as functions into finite sets. Then we can attach all those bells and whistles on there. And the attributed stuff extends this to infinite sets. So like you could put a real number. Insofar as float 64 is a infinite set of real numbers, then you can you do that, stuff like that. So you can kind of put any data structure you can define in Julia, including all the primitive types, all the numeric types, all the array types, tree types, stuff like that. Put all those types as attributes onto your vertices and edges. And we can do simplicial complex. We can do triangles to say like 3 people who live in a house together, something like that, or a teacher, a student, and a parent is like a triangle, and the teacher and the student see each other more often than the parent and the teacher. So you could do kind of higher order network stuff too.
Okay.
Cool.
Just to comment on that. Maybe it's obvious, but the reason why it is interesting to do that using graph rewriting is that the graphs may actually change due to the spread of the disease. So, for example, people go into isolation, and then you take away a connection because people who met before won't meet anymore. So you get a dynamics which is, on the one hand, driven by the state of the nodes, the states of the agents, and that changes the structure of the network, which in turn again has an influence on how the states of the agents change. So you basically get an interplay between the state changes and the structural changes there. So that's
I think that's something interesting, and I really want to give props to Nick, for inviting me to this seminar. He saw my talk at the ACT conference in 2019, and and came up to me afterwards. I was like, oh, this is very interesting. I think all these graph rewriting people would be interested in it. And I had no idea. I read some graph rewriting papers and kind of, Googled it, and it's like, I don't really see the connection here. But now, especially now that we've got CSET rewriting and we've got string diagram rewriting, and it's like, oh yeah, this is, he was onto something before it was obvious to me. So definitely a good eye there. Yeah, and thanks. I see Andrea has posted the link in the chat. So,
So Nick, do you want to comment on that since you raised
Yes,
your hand?
Of course, first of all, James, it's great that you came here and you gave this talk, which I thought back then might have been maybe a bit early, because now you have this beautiful implementation also, which I think has progressed massively the last few years. It's looking really, really great. So thanks a lot for that. And I maybe wanted to, I'm sorry, this is like a really technical question, but I'm personally quite interested in all of these ways you can, what properties do you get from a double push overriding system relative to the category doing this over? Because adhesive categories with presheafs is sort of a sweet spot, because you get actually associative properties. You can actually show that if you do several rewrites, you can summarize these rewrites, by looking at the partial interaction of the rules. But then exactly our limit was for a while that if you want to do, for example, simple graphs, and in chemistry, you often want to do that. Simple graphs do not form adhesive category. So, I was just wondering, because for example, the string diagram people have this nice feature of using selective adhesive categories. You can do simple graphs with conditions on top of them. You can have a category of simple graphs with regular monomorphisms, but that's only a quasi-topos. So I was just wondering, regarding simple graphs, you seem to be indicating you have a method of doing simple graph rewriting. Is that correct?
No. So graph rewriting stuff relies on the fact that the presheaf category is adhesive, and we don't. So something. There are a lot of data structures in computer science that rely on things being ordered, like trees. So I talked about that discrete dynamical systems, right, and I didn't talk about trees or forests.
Exactly.
Because the acyclicity requirement is not compatible with the CSET.
But the question is, I want
to put out. That's why we want to soup up the logic of C. We want that to be like a finite limit theory, or put more into the logic of C, so that the models are more constrained in that way.
So because I think there was already the question about theorem true and before, and so because Reiko and I have been experimenting with, and together with a PhD student of Reiko's also coding graphs in Z3 actually, and we found that if you code these graphs in first order logic and simply implement that first order logic, that seemed to be a viable avenue. It's even sort of for some applications relatively efficient. So I was wondering, somewhere in your framework, and I'm really not an expert on implementation, is there a chance to get, let's say, for example, graphs with application conditions, with constraints that are expressed as first order logic? Because that would be extremely useful.
Yeah, with that.
But maybe impossible. Yeah.
With the so that the attributes kind of, you can just put any Julia type on there. So you could write your first order logic as a tree of however you want to represent that expression, right? So you could attach arbitrary code to each vertex. So that kind of stuff, doing stuff with the attributes is weird. They're often like, how do you want to treat the attributes becomes a design decision, as opposed to the purely combinatorial nature of the CSETs themselves. Right. The objects and the HOMs are pure, like if I renumber everything, it's fine. The attributes is like, well, do I have an equivalence class on abstract syntax trees in Julia? It's like, well, no, I don't have such an equivalence class. Right. So that kind of like, yes, you could always bake it in with an attribute. It's like an escape valve. Like, you can just put anything in there, but then, okay, what's going to work depends on what you put in there. So if you put in, like, if you just put in numbers, it's like stuff's going to work. But if you put in something more complicated, it's a question of like, oh,
Right.
I need to put we'd like to, there's a paper, algebraic databases, that is part of this, David Spivak and I think Christina Veselova. I'm going to mispronounce her name on YouTube forever, but Christina V. And Schulman, I think, had this paper, algebraic databases, and they put like a Lavoisier theory on the attributes. Right. So that we're not there yet, but that would be one step.
And sorry, if I'm allowed one more quick question. So because I'm also collaborating with Joachim, so can you guys do group rates now or combinatorial species?
Groupoid
in the scope of plants, or?
Yeah, so as a you can encode a groupoid as a GAT by taking the GAT of categories and extending it with an involution term constructor that takes every hom xy and gives you a hom yx, such that the composite, like f inv f equals id.
Right.
So you can encode groupoids as a simple extension of GAT of categories. Nice. And so this GAT submodule is really really flexible. So we kind of have two things. We have like full board GATs where like the logic is very powerful, but the implementation is very challenging. Right. And then we have CSets where the logic is very simple. It's just a a finitely presented category, but the implementation is very powerful. So there's this spectrum of we wouldn't be able to implement at the level of we would not be able to implement all of the things we've implemented for CSets for models of arbitrary GATs in the way that we have it for like models of arbitrary categories. So that's kind of that makes sense. Like,
okay.
Models of a category are very simple things. So.
Yeah. So thanks a lot, and also like maybe if you can get us in contact with this student, maybe at some point we could have a follow-up to your talk with the DPO rewriting in your framework as sort of a tool session, maybe.
Oh, yeah,
that would be quite nice. So, yeah.
That'd be good. We can focus on that, and I'm gonna commit him.
Excellent.
In public without asking him. We have this research week for the adjoint school, and I think preparing a good DPO rewriting tutorial as part of that week would make sense.
Very nice.
Hopefully he'll have some time for that soon.
So,
great.
So again, thanks a lot.
Yeah,
it was a very nice talk. Yes.
Yeah, thank you for inviting me, and I look forward to talking to you guys in the future.
Excellent.
Okay, thank you. So shall we close the session then?
Any final questions?
Any final questions? Okay, so thank you very much, everyone, and James in particular. And yeah, we'll keep in touch and explore these things further in the future. Yeah. All right, thank you.
Thank you, everybody. Bye-bye.